Good day. I'm Ernest Piansay, and today I'll be discussing quantum dots as aids in fighting drug-resistant superbugs. So, superbugs, or multi-drug-resistant bacteria such as E. coli, Salmonella, and KPN, are known to quickly adjust to antibiotics by creating suitable enzymes to counteract such antibiotics. These strains are known to be resistant to at least 20 antibiotics, which cost huge amounts of waste money every year. Different methods on potentiating the effects of antibiotics on these bacteria have been done, but a study done by Courtney et al. From the University of Colorado in Denver and the University of Colorado in Boulder made use of superoxide generation of quantum dots. The study implores the aid of reactive oxygen species, which are radicals known to damage DNA. To put it briefly, the superoxide radicals would perturb the cellular redox environment, allowing the antibiotics to take effect. In the study, the quantum dots that were used were cadmium telluride having a band gap of 2.4 electron volts and exhibiting a reduction potential of negative 0.33 volts, just enough to produce superoxide radicals upon illumination and excitation. The confirmation of the production of the reactive oxygen species, or ROS, was done via electron paramagnetic spectroscopy with 5,5-dimethyl-1-pyroline N-oxide, or DMPO, which showed distinct peaks for superoxide and hydroxyl radicals. The direct production of superoxide was further confirmed by the activity of the enzyme superoxide dismutase, or SODB, shown by the overexpression of such enzyme in E. coli and deletion in wild-type strains, shown in the top right graphs. To check the potentiating activity of the radicals, a checkerboard assay was done with bactericidal antibiotics ceftriaxone and ciprofloxacin, and bacteriostatic antibiotics clindamycin and chloramphenicol. Using this independence, it was found that 76.4% of all combinations showed synergistic effects. Meanwhile, studies on optical density showed increase in growth inhibition upon combination of antibiotics and cadmium telluride. To further test the potentiating effect of the superoxide radicals generated by quantum dots, studies on tissue culture and an animal model system were also done to simulate an infection. For the tissue culture, HeLa cells were infected with Staphylococcus aureus and were studied. The same potentiating effect was seen, with a decrease in the colony-forming units of the strain. For an animal study, the nematode C. elegans was used and was infected with Salmonella, which was the strain that showed the highest mortality rate for the nematode. The same potentiating effect was done, and the survival rate of C. elegans was also studied. It showed that in the combination, an increase in the survival rate of the nematode was evident. The skin depth at which the inhibition happens was also studied and is seen in the table in the bottom right. It was found that at an estimated skin depth required for 50 to 75% of growth inhibition, the potential of the combination therapy using LED light is observed. Since this study is the first of its kind, there are still no patents online regarding this study, but two related patents, one utilizing ROS as a means to treat diseases, and one using quantum dots in assays to quantify pathogens, can be seen. These patents show that further studies can be done by improving previous studies on certain topics. Possible directions for this topic include studies on tunable parameters such as size, oxidation potential, and surface moieties. Alternative quantum dots to cadmium telluride exhibiting the same band gap and reduction potential could also be done, and light-activated drug delivery could also be used as a tandem to this technology, so that once light activates the drug delivery system, one can also activate the quantum dot to produce ROS. Lastly, this study can also be applied to bandages to aid wound healing, where the quantum dots could be incorporated to the bandages. So that is all. Thank you.